Good evening, good morning, good afternoon to everybody. It's good to see you all here today, and it is my great pleasure to introduce our speaker today, Jean-Philippe Lessard. Jean-Philippe is Associate Professor at McGill University. He's been there since 2017. He obtained his Ph.D. from Georgia Tech in 2007, where he worked under the supervision of Konstantin Mischaikow. He was then a postdoc at Rutgers, at UV Amsterdam, at Princeton, where he was awarded a fellowship from the IAS, and then he was later a group leader at the Basque Center for Applied Mathematics. He became a professor at Laval University, where he stayed for 6 years. In 2016, he was awarded the CAIMS PIMS Early Career Award in Applied Mathematics, and he's currently CRM Deputy Director of Scientific Programs. His research combines numerical analysis, topology, functional analysis to study finite and infinite dimensional dynamical systems. And as everyone knows, he's one of the co-organizers and co-founders of this seminar series. So it's really, we're looking forward to hearing from Jean-Philippe this morning. Jean-Philippe, it's all yours.
Yes, thank you very much, Jay. So I'm actually going to start with wearing my hat of the organizer. So as many of you know, this seminar has been running since June 2020, last year. And this coming June, we have, we're going to celebrate our first year anniversary. And for the occasion, we invited Charles Pfefferman, who will be giving a talk on some of the research he did back in the 80s, where he actually worked with Raphael de la Llave on computer-assisted proofs and relativistic matter, I guess. Right, so that's going to be in June 1st, and we're very happy that he accepted. And so that's going to be basically to commemorate our first year anniversary of the CRM camp. All right, so let me go back to the actual title. So today I'm going to talk about Cauchy problems, both for PDEs and delay equations. I actually like to talk about these two class of problems simultaneously because I believe they share a lot of common ground in terms of regularity of solutions, in terms of the fact that they lead naturally to infinite dimensional dynamical systems if the PDE that we're talking about is, say, a parabolic dissipative PDE and so on. So I did my PhD at Georgia Tech, and Jack Hale was still there when I was there, and he was really pushing this idea that delay equations and PDE should be really treated similarly, and that's the kind of view I want to take today. I really want to first introduce a bit of background on Chebyshev series, and then go and study first the dynamics of delay equations using Chebyshev series, and afterward move to PDEs and give you some applications. And hopefully I'll try to motivate and give directions to where I want to go in both of these class of equations. All right. So first of all, let me describe very quickly. Many of you guys know already what Chebyshev polynomials are. So these are orthogonal polynomials. They're defined from the interval -1 to 1 into R, and they're defined recursively using this relation. And because of that recursive relation, then you can easily verify that they are in fact Fourier series in disguise, as tk of cosine of theta is equal to cosine k theta. And that leads to very nice properties for those of you who like to use Fourier series, because when we use Chebyshev, then when we take products of Chebyshev series, then their coefficients become discrete convolutions. And that's very nice if you like to work with Banach algebras, because there are very natural ways to treat these nonlinear problems. Okay, and a nice theorem is that every Lipschitz continuous function has a unique representation, has a uniformly converging series, Chebyshev coefficients here with multiplied by the Chebyshev polynomials. And moreover, so if the function is analytic and it's analytically continuable to the row ellipse, then and it's bounded there with a sup norm to be m, capital M, on the row ellipse, then its Chebyshev coefficients do have a geometric decay rate given by m times rho to the minus k, where rho is the side of the row ellipse. So for instance, some row ellipse are here when rho equals 1.1, 2, 4, 2 pi, and so on. So it can be obtained under the image of that map here. Okay, so let me just give you, I kind of like this example because it's very simple and it's an ODE. So if you try to solve that ODE both with Taylor and Chebyshev, you can see already that Chebyshev has some advantage in terms of decay of the coefficient. So say that I want to solve that problem on the interval -1 to 1, okay? Where t is between -1 and 1, and let me take the initial condition to be 1/2. Then I'm going to use Chebyshev expansion to compute that. And by plugging the Chebyshev expansion, then I do get that problem to solve, this zero fighting problem, where that kind of tridiagonal operator comes from the fact that, well, when you integrate the Chebyshev polynomial, you get the neighboring Chebyshev polynomials. I mean, yeah, if you integrate tk, then you'll get tk plus 1 divided by something and tk minus 1. Anyway, so if you solve that zero finding problem, you'll have the Chebyshev coefficients of the solution, which is in fact given by exactly this solution, which has poles at plus and minus I pi. So now keep in mind that I'm restricting myself to the interval -1, 1, because I also want to use directly Chebyshev polynomials. I could rescale and that would not be a problem. Okay, and the thing is that, so you can see that for this problem, there are poles at plus and minus I pi because of the solution here. There's a pole because of the denominator being 0. So if you see, you can clearly see that the Taylor coefficients will decay as a constant divided by pi to the k. Whereas if you look at this, we can fit the row ellipse up to 2 pi, which means that the decay rate of the Chebyshev coefficients will be a constant divided by 2 pi to the k. So there's quite more decay in the solution of the Chebyshev coefficients. So that's one way to see it. Of course, there are gazillions of ways to actually compare the two. But you can see here that decay-wise, Chebyshev is a clear winner. It decays much faster than the Taylor coefficients. Some may say that Taylor leads to easier formulas, fair point. But if, say, you have an approach that handles generally the fact that you have these discrete convolutions and you have these tridiagonal type operators, if you have a general approach, as Florent Bréard often described, he gave a talk about this, then there's very nice decay and the approximating properties are beautiful. And well, I like this quote from John Boyd. I'm not going to read it all, but let's say there is one thing that I like, is that unless you're really, really sure that another basis is better than Chebyshev, then use Chebyshev polynomials. Of course, there are problems in higher dimensions and different PDEs with different geometry. That's not possible at all, but when you can use them, then use them. And one thing that I can say is that before moving now to delay equations, then it's really not new that people have been using Chebyshev polynomials in the past, I would say, what, 15 years or 10, yeah, okay, 10 years, 10 to 12 years. And yeah, I was mentioning Florent and then Miyawara as well. They've been working with Chebyshev since 2010 already. And many people since then started using them to obtain computer-assisted proofs in linear ODEs and in nonlinear ODEs as well, and so on. All right, so now I want to talk about two applications I mentioned at the beginning. So I want to talk about delay differential equations and parabolic PDEs. And I'll be starting with delay equations. And I may spend more time talking about delay equations today than about PDEs, we'll see. And this work on delay equation is joint work with Jay, Meredith James from FAU. And yeah, so let me actually describe it. So our setup is the following. So we have a delay differential equation. It's a system, okay? It's a system, and here I'm making a disclaimer. This is for the moment working for constant delays. Of course, we are aiming to deal with more complex type of delay equations, but we somehow need, in this context, we need a flow. Okay, we need a semi-group or kind of a rule. And for some problems, it's not so simple, but for the moment, this is the setup, right? So we have a constant delay, tau, here it's a constant, and f is smooth. And what we propose is a C1 time-stepping Chebyshev scheme. Okay, and what we want to do is that we want to treat that as a discrete dynamical system. We'll see. But first of all, let me just emphasize that delay differential equations are hard because they naturally lead to infinite dimensional dynamical systems. So if you look at this cartoon, well, it's actually a movie of an integration of Wright's equation, which is here with parameter value alpha equals 12/5. So Konstantin Mischaikow talked about it a lot some weeks ago in the CRM camp colloquium. And I mean, in his talk, you could appreciate the complexity and the hurdles present in studying this model, because it's infinite dimensional. And why is it? Because if you want to move forward in time, then you need the history from time, say, 0 to minus tau. At each instance, this is what you need, right? You need the history to move forward. So what you see in black here is really you can think of it as the element in the phase space, which in that case is the space of continuous function from minus, well, tau to 0. Tau here is 1. Okay, so if you want to make a more standard phase space picture of this, then you could think of y0 as the initial condition here. It's a point, and then it moves toward what we call a slowly oscillating periodic solution here. And each point here is in the Banach space omega, which is the space of continuous function. Okay, so that's why they're hard, and that's why they are. I mean, many people are interested in this. Of course, right now there are these state-dependent delay equations that people are interested in. They definitely contain lots of theoretical difficulties. So for the moment, theoretically, there's not a lot that we don't understand in terms of the general theory of constant delay equations. But still, if you give me, or give an engineer, or you give a scientist a model with many nonlinearities, then to actually prove things about the dynamics of these delay equations, even if they have constant delays, that can be hard. And so what we propose here is to really solve forward initial value problems. Well, in the end, we will be interested in periodic orbits and in connecting orbits. So it's not quite what we really want to solve Cauchy problems, but still, I'm going to present it like that. And recent and earlier work on integrating delay equations go back all the way to work of Mischaikow in 2010, where he used, together with Minamoto, linear splines to integrate forward in time delay equations. And then in a paper in 2014 by Tibor, Kristin, and others, then they actually studied Wright's equation and the generalized, the Wright's conjecture. And in that process, they actually they did piecewise constant representation of solutions, which they integrated forward. And we did something similar in 2017 to study Jones' conjecture together with Jonathan and Konstantin. And afterward, a little bit afterward, and Rai Scherbarsky, a PhD student of J.B. Vandenberg at the VU in Amsterdam, in his thesis, he actually wrote down kind of the basis, which is kind of obvious from our perspective, but we kind of pushed it more toward discrete dynamical system. But already in 2018, that was kind of present. The ideas of the talk of the first part of the talk of today, and also of course the work of Piotr and Robert on forward integration of delay equations in the first papers in 2018, and I believe they're working right now on improving this, and they use piecewise polynomials, and they apply their approach to study Mackey-Glass equation, which I will also talk about today. Okay, so how do I want to treat this problem? I said kind of very briefly that I want to treat that as a discrete dynamical system. So let me be a little bit more explicit about it. So let me define, or to consider, an initial condition, y0, which is going to be a function which is continuous on the interval minus tau 0 into Rd. That's an initial condition. And the solution y1 is a solution if it is the unique solution or the unique fixed point of that operator here. Okay, so all I have to do here is to treat the history here as my initial condition. That's why it's my history. This is given. And now I want to solve y1 by integrating basically the delay differential equation, and I'm looking for the fixed point of that. So if I have a fixed point, y1 of t of y1, y0, then I do recover the solution now, but from the interval 0 to tau. So I start with y0 from minus tau to 0, and I obtain y1. So theoretically, this is a no-brainer because it's like solving a non-autonomous ODE, right? Solving forward the non-autonomous ODE. So this is kind of the theory that leads to the fact that there is a unique fixed point to that operator is there. Okay, so say that's my y0, and then I solve uniquely the fixed point t1, t of y1, y0 equals y1. Okay, so that gives me the image under that kind of that process. And what I will talk about, I mean, the way I will describe this map, I will describe it as the step map. So the given y0, there exists a unique y1 for which I have my forward solution. Okay, so this is theoretical, and that's often called the method of steps. That's one way to recall to rewrite the so-called method of steps. Okay, and you can apply that many times. So say that for Wright's equation, you take an initial condition that's for alpha equals 3, and you can just move forward, and that's the step map. It gives you always the solution on a time interval of length 1, because the delay here is 1. Okay, so that's just a cartoon. And what we want to do now is that we want to actually study that from the perspective of discrete dynamical system, but we want to do that using Chebyshev series to represent solutions. Okay, so once we have all of these, the step maps, then you can recover a long solution. So let's say you'll have a k steps solution, y, which is defined from 0 to k times tau into RD. It will solve the DDE with history y0 if and only if y is given by that, by basically the image under the step map. So that really leads to a discrete dynamical system. So that's why now we want to kind of move toward thinking of delay equations in this class of problem, but we want to think about them really as infinite dimensional discrete dynamical systems. Okay, so let me just recall that we have the step map, which is given by f of x equals y if and only if y equals t of yx uniquely. Okay, and what I will do is that I rescale the interval 0 tau to -1, 1, because as I said, I want to discretize the step map with Chebyshev polynomials. Okay, so that's why I do the rescaling, and that rescaling leads to a new fixed point operator with the tau appearing there. And now it's for t between -1 and 1. So now given a history x, or given just an initial condition or a point, a function, defined on the interval -1, 1 into RD, then I'm looking for y, a function, again, in the same space, also defined on the interval -1, 1. Okay. So then what I do is that I plug Chebyshev series in that integral equation, or that's fixed points. So say the Chebyshev coefficients of x are given, they're known, and then I'm looking for the unknowns a0 and all the way to a infinity. And that leads to, by plugging that in, then that leads to this zero finding problem here, which has kind of similar, structure than already the simple logistic equation that I showed at the beginning to compare Taylor and Chebyshev. They were these tridiagonal terms, and that's the same thing here. Okay, and the f sub n's are nothing else than the Chebyshev expansions, the Chebyshev coefficients of the map F, which is the vector field defining the delay equations. And as I said before, if we do have say some polynomial nonlinearities, then the fact that we're using Chebyshev series, which are Fourier series in disguise, then these coefficients will be discrete convolutions. And that first condition, to be equal to 0, is there to ensure that I have continuity of the solution. So at the edge, say maybe here, yes, so that I do have that y2, say at -1, is equal to y1 at +1, and so on. So this is kind of ensuring that I do have continuity. Okay, but as we know, and it's not hard to convince yourself that as you move forward, the step map actually gives you more and more regularity. But it's kind of natural to treat delay equations as infinite dimensional discrete dynamical system, because the smoothing is discrete, right? So if you start with a function which is C0, then after one step it's C1, and then C2, and then C3. So that's this kind of discrete regularization, whereas, for instance, for parabolic PDEs, this regularization is instantaneous, but it's still kind of, again, going back to the ideas that Jack Hale was comparing delay equations and parabolic PDEs, that's still kind of a nice analogy. All right, so now we're looking to solve for the zeros of that function. So given B, the Chebyshev coefficients of the history, solve for A such that FAB equals 0. And we have seen that many times, so I will not give too much details here, but we do solve that problem using a Newton-Kantorovich type theorem. Some people call it the radial polynomial approach. So yeah, so basically, yeah, this is very general approach, which is used in very different contexts. And for this, we have, in that case, I kind of rewrote it in the framework of the problem at hand, which is the one with given B, I want to solve A such that f of AB equals 0. So we have to find an approximate solution by first considering a finite dimensional projection of that map. So we consider only finitely many Chebyshev, finitely many functions, and then we compute an approximate solution, A bar, of that problem. And once we have this A bar, we compute an approximate derivative of the Jacobian matrix. And then we define what we call an operator A dagger, which is an approximate derivative using the structure of the problem, an approximate inverse A. And we compute these bounds using interval arithmetic. And then if we can show that there exists a positive R or R0 such that this is negative, then we do have a contraction of a Newton-like operator nearby the approximate solution. And therefore we have a true fixed point of that Newton-like operator. And by construction, we do have a unique zero of f A tilde B equals 0. Okay, so yeah, so this is kind of a common tool in this seminar. So I'm not going to spend much time on it today, but for those of you who are not so accustomed to it, this is really, these bounds are there to show that a Newton-like operator has, if we do define a Newton-like operator close to an approximate solution, and the Fréchet derivative of that Newton-like operator in the neighborhood of the solution has an operator norm less than 1. And that operator norm less than 1 is the contraction constant, which will ensure the existence of a unique fixed point. So our Banach space in this case is a Banach space of weighted L1 Chebyshev coefficients with geometric decay. So if we do have, say, if we start with, say, with an initial condition which is analytic, then the solution will remain analytic, and we can use the fact that solutions which are analytic have exponential decay rate to design the function space or the Banach space for which we will apply our contraction mapping theorem to encapsulate this decay rate. Okay, so as I said, I will not give much details about computer-assisted proofs, or I mean how to compute these bounds, but it's quite a bit of analysis. There's a lot of papers that could refer the interested people to. But for the moment, just a simple example. So that would be for Wright's equation. Say we start with an initial condition, which is close to 0, it's constant. And then we apply the step map. We solve the zero finding problem using the radial polynomial approach. And then at A1, there exists, I mean, we get A1, and now instead of Y1, I describe A1 as the sequence of Chebyshev coefficients representing the solution of the step map, the image of the step map. And there is an error of 6 times 10 to the minus 15. And I take that as an input, I apply the step map, now I solve for f of A2, A1 equals 0 using the radial polynomial approach, and then I get an error bound of 6 times 10 to the minus 14. But as you can see, well, I managed to get all the way to 14 steps, so that's a rigorous computation, but the wrapping is terrible. It's terrible because, well, we didn't think hard about it because we did not really have in mind to do initial value problems. That's why the title of this talk is a little bit misleading in the sense that it's more like dynamics of PDEs and delay equations using Chebyshev series. But anyway, so yeah, so it deteriorates, but if we set it up properly, then we can compute very long orbits without having this wrapping effect. All right, but the Banach space that we used in this case, so it's a one single copy because it's Wright's equation has only one scalar function, so solution. So these are the Banach. This is the Banach space we used. We used a weighted L1 space. We put the 2 there because with the 2 there, that norm leads to a Banach algebra under discrete convolution. And if you think of this as say B times A, then that's going to be just a discrete convolution of A times B, and that Banach space here will kind of nicely deal with the nonlinear analysis coming from the fact that, yeah, that we have a Banach algebra under discrete convolution. Okay, so that's just an example, but that's really not the kind of things we want to be studying. So what we are interested in fact, is more about the dynamics. I will talk about really our goal which is really toward things concerning, say, for instance, the dynamics of the Mackey-Glass equation. I think Professor Michael Mackey is here, which is an honor. So we are interested in kind of proving things about Mackey-Glass, and let me get there slowly. So the kind of things we can prove with the current approach is what we call m steps periodic solutions. So take a number m, and we say that the differentiable function is an m step periodic solution of the delay equation if psi is a solution, and it is a solution with a period which is an integer multiple of the delay. Okay, that's what we call an m step. And if we have an m step periodic orbit, then it will be a solution of this larger zero finding problem, which makes sure that, okay, so if I solve, so that's the zero finding problem here for the step map. That's not the same as the step map, right? So if I go back here, so this is the zero finding problem that given B, if you can solve A such that f of AB equals 0, then you have kind of solved, then A is equal to the image under the step map of B in terms of Chebyshev coefficients, right? So if I solve this to be equal to 0, then that means that A1 is mapped to A2, and similarly, A2 is mapped to A3, and then AM minus 1 is mapped to AM, and AM is mapped back to A1. Okay, but in that case, if you think about it, an m step periodic solution given, for a given delay equation, this is not something that should be generic, right? It should be isolated. So that's why what I decided to do is that if you have a parameter, so in the Mackey-Glass, there are several parameters. In Wright's equation, not so many. In Wright's equation, there is alpha, and you could think of alpha as being also equivalent to some sort of the delay moving, but there is really one parameter in Wright's equation. So let's say if you have one parameter, then you can solve for the parameters so that for given n, you do have an m-step periodic solution. Of course, it may not be there, but if it's there, then by solving for the parameter, you may be able to find it. So that's why I leave here the tau as a variable, because we kind of have to solve for a parameter for this to happen. And also, it's natural in the sense that periodic orbits have that shifts of periodic orbit give another periodic orbit. So that means that we have to kind of also impose some sort of phase condition which balances for the tau. Anyway, so now we have this large zero finding problem, so that a zero of that larger zero finding problem is in fact an m-step periodic orbit. So now we can use the same idea, but now we just have a more complicated problem. Let's say given a delay equation, we solve for the zero of that big map. And once we have a zero of that, we can use the radial polynomial approach, or the Newton-Kantorovich type theorem to obtain a solution. And then after that, we do have an m-step periodic orbit. Okay, so yeah, I already kind of mentioned that. We impose a phase condition, and we can use computer-assisted proof to solve this. So let me go to some applications. So that's a computer-assisted proof of a 12 steps periodic solution in the Mackey-Glass equation with alpha equals 2, beta equals 1, and rho equals 10. For this, we used 60 Chebyshev coefficients per component. And in that case, well, we had to, in that case, it's non-polynomial. So what we did was to kind of introduce a higher dimensional delay equation, which contains polynomial nonlinearities, and we applied our approach to that higher dimensional polynomial delay equations. And at the end of the day, if we prove something about the dynamics of that equation, which has now, I think it was a 4-dimensional polynomial delay differential equation. So one of the components of that higher dimensional polynomial delay equations gives me the actual solution of Mackey-Glass. Okay, so some people would treat the nonlinearity directly. We often choose to we often choose to actually solve it using that approach. Okay, so there's a question from Elena saying, do the periodic solutions in DDEs always need to have period an integer multiple of the delay? The answer is a big no, absolutely not. And so that's why this approach, I mean, we've thought about kind of introducing a small shift to actually make it more general. But in some sense, for what we're trying to do right now, it's sufficient. But the answer is no, Elena. This is absolutely not. Yeah, you could also use Fourier series, absolutely. So Javier, this is a very question on point. So we can also use a Fourier series for this. Okay, so we actually did use Fourier series, and that's work with JB and Chris. So for periodic orbits alone, then using Fourier series is actually a very good approach. So these are two periodic orbits that we proved using Fourier series in the so-called chaotic regimes in Mackey-Glass equation. Okay, and but that's that the periodic orbits with Fourier series is really going to give you only periodic orbits, right? What we're after is really to try to compute more than that, and I'll come to it in a minute. But yes, absolutely. So Javier, this is absolutely right, and that's an example here. Okay. Yeah, that was very timely, very interesting timing. All right, but so let me just go back here. So let's say this is a periodic solution we proved, but that's a very long one in some sense. And some of these periodic orbits that we managed to prove with Chebyshev, well, we were kind of struggling with Fourier. So there could be a small advantage, but I don't want to describe this here. I want to move to really what we're aiming at. And here's another periodic solution, and a 6 steps periodic solution in Mackey-Glass. And that's really in the same parameter regime. So alpha equals 2, beta equals 1, and rho equals 9.65. And these, I believe, are the parameter values that were used in the original paper of Michael Mackey and Leon Glass, where they observed numerically chaos. Okay, so what is the goal here? Why are we doing this? Because, yeah, as you can see, we could also have used Fourier series. So this is an orbit which is kind of present. Yeah, so if we do a numerical simulation in at parameter value tau here, then you kind of see or observe some numerical chaos. So what is our goal here? We're not only after periodic orbits, because if that was the case, I would be using Fourier. Now we're really after I like using Poincaré scenario now, because this is kind of, I was in Szeged some years ago, and the first plenary talk was given by Hans Otto Walter, and he described, how complicated the dynamics of delay equations can be, and he used the terminology or the expression Poincaré scenario, and in fact, he described that possibility of Poincaré scenario in Mackey-Glass, right? And he mentioned that was still an open problem. And that the scenario is the following: so that chaotic motions, they may arise from the existence of a homoclinic orbit attached to a periodic orbit. So that really is what we are after, and that's why we have designed this approach somehow. That's how I like to think about it. I mean, the step map approach is more general. It's for delay equations in general, but this is really what I have in mind. So that's the kind of thing I'm interested in. So we have lots of things to do, but lots of things are already done. So in order to prove the existence of Poincaré scenario in Mackey-Glass, then we have to do several things. So first of all, to make sure that the homoclinic exists, and we believe we have found it with my PhD student Olivier Hainaut and Jay. So we have numerical evidence of a connecting orbits attached to a periodic orbit. But now the question is, can we find one attached to an M-step periodic orbit? And we also believe we have it. In fact, I believe this is the one that yeah, I would have to double check with Olivier, but I think there is a homoclinic orbit attached to this periodic orbit, because that's kind of in the chaotic regime. So the next step is what? The next step is actually to prove the existence of that periodic orbit using the method of steps. So this is done, and now to compute the unstable manifold of the periodic orbit. But now the unstable manifold of the periodic orbit, now this is the periodic orbit is a M is a fixed point of the mth iterate of the step map, right? So then we can think of studying the unstable manifold of the discrete dynamical system of the fixed point of p to the of f, say, to the m, the mth iterate of the step map. Okay, so this should not be hard. We have not done it yet, but this is work in progress. And then after that, we want to compute the infinite dimensional stable manifold of the periodic orbit. And that's really where the motivation for this step map approach coming into play, because now we have an m step periodic orbits, which is the fixed point of f to the m. And now f to the m is a compact map on the space of Chebyshev coefficients. And Jay and Raphael de la Llave, they have a paper where they study the stable manifold of fixed points of compact maps. And now we believe that we have kind of, I mean, that with our current setup, then we do have, access to say a theory that will allow us to compute a stable manifold of that m-step periodic orbits. And once this is done, then we can solve a boundary value problem, a projected boundary value problem, making sure that we start in the unstable manifold and we end up in the stable manifold, and we solve it using the method of steps, basically with a similar map as the one for periodic orbits. So here we see a picture of Michael Mackey and Leon Glass, and actually I think it was used in a conference recently commemorating their work and their achievement. And being at McGill, of course, it's very motivating to work on that equation since it was introduced so long ago. And they don't work in the same building than me. They work more uphill at McGill. I'll actually show you their building at the end. We're more downstairs, down the hill at McGill. So I don't see them often, but it's always a pleasure to discuss with them. Anyway, so that's okay. So the step at the end will be to solve a projected boundary value problem. And I want to give you an example that in fact we can do that. So let me do an example of connecting orbits and delay equations. I was trying to finish that example last night, which I almost did. I was kind of getting toward the Z1 bound, but finally I didn't finish it. I decided to go to bed. But this is a joint work with Blake Barker, Kevin Church, Jonathan Jackett, and Jay. And I'll just show you basically an application of this step maps approach to compute the connecting orbits. But what we have in mind for this project is to study a delayed PDE, and that delayed PDE has traveling waves, and we are interested in computing stability of traveling waves using Evans function. So this is an ongoing work, but that process of computing the stability of the traveling waves requires first computing the traveling waves. So if you plug a traveling wave ansatz in that delayed PDE, then you do have to solve a connecting orbit for that system of delay differential equation. And that delay differential equation has two fixed points, one at 0, 0, which is stable, and one at 1, 0, which has Morse index 1. And a traveling wave solution is in fact a connecting orbit between 1, 0 and 0, 0. So that's a connecting orbit in an infinite dimensional dynamical system. So I'll not talk about the stability of the traveling waves with the Evans function. This is completely outside the scope of the talk, but the point is that we need a good control of the location of that traveling wave in order to compute other things, in order to compute, say, the Evans functions, and we have to go from infinity to plus infinity, compute some quantities, and that requires good control. Okay, so as I mentioned before, so using a similar approach and for the m steps, and we can actually compute the connecting orbit between two steady states in that case by solving a zero finding problem. And what I want here is that I want that the first part of my initial condition of my projected boundary value problem is in the unstable manifold of 1, 0. So Jay and Chris Rutgers, they actually wrote numerical papers a while back where they showed how to numerically compute parameterization of unstable manifolds in delay equations. And recently, we together with Olivier Hainaut, my PhD student, we actually made that. We obtained computer-assisted proofs of unstable manifolds, and it's very similar to ODEs. We have to solve these recursive formulas, and then we can obtain Taylor expansions. But now well, maybe I will not give too much details here, but yeah, we can compute the unstable manifolds. And once we have that, then we make it part of the big zero finding problem, where if you have, say, that A1 minus P at sigma is equal to 0, then you're sure that the first initial guy is in the unstable manifold. And then after that, you do as before. You want to map A1 to A2, A2 to A3, AM minus 1 to AM. And at the end of the day, because this problem has a specific structure, then 0, 0 is stable. And so locally, the stable manifold is full dimensional. Well, it's infinite dimensional, but Kevin and Jonathan, they worked on designing and computing a trapping region. So that's phase condition here is kind of simple. It imposes, it's codimension 1 phase condition that imposes that I'll be in the stable manifold. In other words, it's more like a trapping region. Okay, so this is a numerical, it's almost a proof. Probably it's 3 hours away from being a proof. But you know, I did the unstable manifold with Newton-Kantorovich, and this is done. And then you know, the zero finding problem is done. So here I have m steps. So let's say what you see in green is the unstable manifold. It does an amazing job. I used 100 Taylor coefficients for the unstable manifold with, I guess, the error bound for the unstable manifold was something like 10 to the minus 13. Which is great. And then I use that as basically my initial condition. So A1 here is equal to the value in Chebyshev of the most right point of the parameterization. And then I make sure that I solve all of these intermediate problems. So all of these red, blue are going all the way to an epsilon, which I fix in that case to be 2 times 10 to the minus 6. So I'm 2 times 10 to the minus 6 away from 0, 0. And I used 20 Chebyshev coefficients per components. And that was at these parameter values. So the wave speed is 1/2 in that case. So that's an example of, say, a projected boundary value problem that we can solve using these techniques and using the step map. And that's kind of hopefully what we're going to be using at the end to prove the existence of homoclinic orbit attached to a periodic orbit, using that IDA that we can use discrete dynamical systems and Chebyshev series to get that. And hopefully that proof, if we make it happen, then you know that will yell we'll get transversality out of that proof because of the contraction mapping theorem. Okay, so that really is where we are going with that. Because otherwise, to go back to Javier's comment, then why not use Fourier if you're after periodic orbits? And that's a very fair point. And I would not be able to argue for a long time that that's the best ways to use Chebyshev, because m steps orbit are kind of a little bit restrictive, right? On the other hand, we're thinking also of introducing in that big map a shift in order to make it more general. That's ongoing project, so that's kind of an open problem. All right, so this is the part I wanted to talk about on delayed differential equations, and here are some references. Here are some references for the work that I've been talking about. Most of them are pretty recent papers. Most of them just appeared. Okay, so I want now to move back to move to PDEs, and more specifically parabolic PDEs, but with a similar approach, with a similar idea. Now, I do not want necessarily to think of infinite dimensional discrete dynamical system, whereas it is in some sense what it is, but it's not as natural. There's more choices to be made, and for delay equation, it is clear coming from the value of the delay, whereas for PDEs, it's more like choices, it's more parameters. But okay, so this is joint work with Jacek Siranka, who is now at the University of Warsaw. And so that's been a subject of interest for many people, this idea of trying to solve rigorously forward in time Cauchy problems associated to PDEs. And going back all the way to the work of Piotr in 2004, with his work on covering relations of consistent bounds. So he really is a pioneer in this field, and we must give him a lot of credit for pushing lots of ideas in these directions. And afterward, in 2010, so Hans and Gianni, they proposed a C1 integrator. So the advantage there was that they could get stability results for some periodic orbits in Kuramoto-Shevashinsky, and they used analytic norm. They used somehow very similar norms. I mean, in some sense, exactly the same norm as the one I'm going to use today. So I have to give them credits. And then they use variation of constant, and so that was published in SciAds in 2010. And then Professor Oishi, who was our speaker recently, and Akitoshi Takayasu, he was also a speaker. So they have a very beautiful approach based on semi-group and evolution operator. I think they first applied that in 2017 to linear equations, and more recently, they, together with Jonathan and Professor Okamoto, we actually did it with Chebyshev, but not quite with the same approach as today. But we also used the semi-group and evolution operator. And it's important to also mention that Jacek kind of adapted a little bit the approach of Piotr. And together with Tom Vanner in 2018, they proved the existence of connecting orbits in Oita Kawasaki, going from a saddle to a sink. So they integrated long enough to end up in a sink, in a trapping region, a little bit in similar fashion as I did with the Kobayashi model that I just presented before. And so Jacek kind of used similar ideas than the ones of Piotr. But I believe he had some, say, FFT, or I think he used the sophisticated techniques, making some parts more efficient. And finally, needless to say that the recent result of Piotr and Daniel on the chaos in Kuramoto-Shevashinsky is also worth mentioning. And Daniel talked about that, in fact, last semester. All right, so lots of people have worked on that, and we are not claiming we are reinventing. We're presenting something completely new, but it is new in the sense of the fact that it is fully spectral. And I'm not claiming at all that this is beating any of them. In fact, this is kind of still at the point where we are looking for improvements. And I believe we are getting there. And I personally like the approach I'm going to talk about today, because I tried for so long that, just for the sake of my own ego, being able to finally do something about it makes me feel good. But I struggled for so long that I finally have some results. So, okay. So then another disclaimer I must emphasize is that this is not fully general yet, in the sense that we have this class of PDE. So it's U sub t equals a linear part. D is the highest derivative in the linear part, and n is the derivative of the nonlinear part. Okay, and we have this constraint here that d is greater or equal than 3n. And for the moment, we do not know how to get rid of that condition. Okay, and roughly speaking, this condition is there to ensure that in the space of Fourier-Chebyshev coefficients, so Fourier in space. So here, keep in mind, I'm going quickly here, but x is really 2 pi periodic, sorry. So we're gonna use, it's 1D for the moment, but that's probably not, that's fine. It could be higher dimension, but yeah, we're going to use spectral method. So Michael, yes, we're using spectral method. So, we cannot use at the moment in this setup non-spectral approach. I see your question coming, Michael. Anyway, so roughly speaking, the fact that this condition is there is to ensure that in the space of Fourier-Chebyshev coefficients, this operator here is invertible, and it's also, you can obtain bounds on it. Okay, so for the moment, we don't know how to get rid of that, and I will briefly mention that that's kind of something we want to get rid of. But that said, this condition still contains many of our dear PDEs, at least in this community, right? Fisher, Kuramoto, Swift-Weinberg. And I mentioned the PFC equation because at McGill, that's kind of a big deal. People in material science, they really do like this equation. So there are models of interest that do fit in that class. Okay, so that's the class of problem we are interested in. Okay, so what do we do? Well, we plug Fourier series and we obtain an infinite set of ODEs, okay? And the eigenvalues lambdas are, I mean, basically the eigenvalues of the linear part. So they have like they are of the form k to the power d plus other things, and they satisfy, since the PD is dissipative, they satisfy the real part of the lambda k's are going to minus infinity. Okay, and okay, so what I want to do is I want again to discretize in time using Chebyshev. So now I want to solve this PD, this Cauchy problem, or on PD. This is like the discretization in Fourier, but that's equivalent. I want to solve forward for t between 0 and h. So in time, now I'm rescaling time to be going from 0h to minus 1, 1. And I have, very similarly to the case of delay equations, I have a new integral equation, which I solve using Chebyshev, and that leads to this zero finding problem. Okay, so now this zero finding problem still has, if you remember correctly, in the Taylor-Chebyshev example and in the formulation of the zero finding problem for the delay equation, it still has this shift, these tridiagonal terms as, okay, so J is the Chebyshev index here. J is the Chebyshev index, where K is the Fourier index. But if you look at this structure here, at least in terms of the kind of mathematical problems where I am accustomed to, so often we have this nice tridiagonal structure, but we have that the blocks are eventually asymptotically diagonal dominant. So that's a concept that Professor Oishi emphasized a lot in his talk on periodic orbits and delay equations some weeks ago. And that's exactly what is not present at infinity here. As the number of Fourier blocks goes to infinity, then the operators become less and less asymptotically diagonal dominant. And in fact, they become diagonal dominant at infinity. So there's some structure here that is not present anymore in that kind of operator. So the linear operator here is really the one, so that we're going to study. And okay, one thing that I'm not mentioning, but you know, if you define n tilde to be d divided by 3 minus n, which is greater or equal than 0 by assumption, then we can divide by that number in order to get to kind of kill the, I mean, we can kill the k to the power n in front of the nonlinearity to actually get something out of the, I mean, to kind of get rid of the unbounded term in the nonlinear term. Okay, so once we have this linear part, then we can, I mean, we can more densely write the zero finding problem as follows. So for each Fourier block, we have an infinite, so the LK is an infinite operator acting on AK, and AK is going to be represented by an infinite sequence of Chebyshev coefficients. And the lambda is given by the tridiagonal operator, and the LK is basically that operator that I had before. So this, again, as K grows, then, I mean, the diagonal for fixed K, the diagonal here is 2J divided by K to the D third. And as for fixed K, this is going to be asymptotically diagonal dominant. So we know for small K's, we know how to handle the inverse of that operator. But as I said before, as K gets larger and larger, that's becoming harder and harder. Okay, so I can kind of regroup all of these operators together. And now I have a zero finding problem, which is now A is corresponding to A0, A1, A2, and each AK is an infinite series of corresponding, sorry, it's an infinite sequence corresponding to the Chebyshev coefficients of AK. And so L0 acts on A0, and then LK acts on AK. And this is just a way to represent the operator, but that comes from the fact that I divide by K to the n tilde, and lambda is all the lambdas, which are the tridiagonal operators. So I have a very densely represented zero finding problem for the solution of the Cauchy problem. And once I have that, then I can write, and now this is kind of a trivial reformulation. So if L is boundedly invertible, then I can look for the fixed points of that. Well, it's not Newton-like. Well, it's Newton-like, but instead of taking an approximate inverse of the Frischet derivative at an approximate solution, then L is just the derivative at 0 if you go back. So basically, we just compute L inverse. I mean, compute, we will put our hands on it. But once we have this, if you look carefully, if you write down this A minus L inverse f of A, this is exactly given by that. So we are looking for the fixed point of that Newton-like operator. Okay, and again, we use similar Banach algebra space, and then we use now the space of Fourier-Chebyshev coefficients, and we use now the radial polynomial approach for that. But for this, we need to show that L is boundedly invertible. So for small k, the small k may be the mu k's, I guess they were mu k is minus h divided by 2 times lambda k. So they may be negative for small k. And what we can do is that we can use approximate inverse, Neumann series argument, and computer-assisted proofs to bound the norm of the inverse of Lk for small k. Okay, this is what we did. And for large k, we can use Sherman-Morrison formula and explicit recurrence relation for the tridiagonal operator to find the inverse of the tridiagonal operator. So that's coming from a work that Jacek did with Mucha in 2018. And this is, at least as far as I'm concerned, this is the hard part. And we're working on getting, this is done, but we're looking for simplifying this approach. But basically using explicit recurrence relation, we can compute exactly the inverse of that tridiagonal operator, which we can then combine with Sherman-Morrison to get explicit bound on the norm of Lk inverse for large k, asymptotic bounds for Lk inverse. Okay, so using that, then we can actually compute a bound for L inverse, the norm of L inverse, and then we can use similar approach than the one of the Newton-Kantorovich, but in that case, it's much simpler because if you look at the derivative of the Frichet derivative of t, in that case, because of the structure, which is so simple, then this is bounded away from above by h times the norm of L inverse times the Frichet derivative of the nonlinearity. And h, if you take h small, and if L inverse, the bound of L inverse does not misbehave, then there is a hope that you can have contraction coming from the fact that you have h, which is not so small, not so large, sorry. Okay, so let me give examples and let me conclude. So first application, so Fisher, right, we took an initial condition of, well, u0 equals minus 0.1 plus 0.02 cosine minus 0.002 cosine 2x. In that case, there are 3 unstable eigenvalues, so it's kind of it's a little bit stiff, the problem. And we performed 7 integration steps, and we moved basically from, I mean, there's a steady state there. We started from the steady state, I guess. Is it true? No, I don't think so. No, sorry. Now that's the initial condition, and we integrate forward, and then we could get 7 steps at alpha equals 7.1. Same thing with Kuramoto. Then in Kuramoto, we actually considered the parameter regime where we have chaos. Alpha equals 4 divided by 150. Alpha is here. And in that case, we had 6 unstable eigenvalues. So again, this is kind of stiff problem. So the beauty of Chebyshev coefficients, of Chebyshev polynomials, is that they really handle well stiff problems. So that's great. And we could perform 6 steps, and I will show why we cannot get really far. And that's a really similar problem to the one that we have in Wright's equation. But the example I gave you is the fact that the way that we set up our time stepping approach, then we do not handle well the wrapping effect. Okay, so you can see here for Kuramoto, then the first, after 1 step, we have a rigorous error bound of 10 to the minus 13, but then it quickly deteriorates to minus 11, minus 9, minus 7, minus 5. And that's due to the fact that essentially at each step, we kind of lose accuracy because of the norm of the inverse being large. Right, so then we kind of lose that in an exponential fashion. But there is hope that, well, I'll talk about it later. So for Swift-Hohenberg, we took, that's a cubic problem. We took an initial condition close to the unstable manifold of 0. Well, close, like it's cosine, the unstable manifold at 0 at alpha equals 8.1. It's a 1-dimensional unstable manifold, and we moved from that unstable manifold almost, so the black is the steady state. So we could almost reach the steady state after 7 steps. And so there is kind of hope that we can use that approach together with the parameterization to actually get connecting orbits. In that case, we would need to get to the stable manifold of the steady state. And then in that case, we could use, hopefully, the approach of Jonathan Jacquet, J.B. van den Berg, and Jamie James on stable manifolds of PDEs. And the last one is the PFC equation. So there are 2 unstable eigenvalues here, 40 and 124. So that's pretty stiff, and we could still kind of get long orbits. But again, because of this wrapping effect not being well handled, then that's kind of limited at the moment. But still, we can get some nice solutions, and that's a fully spectral approach, like using Chebyshev Fourier approach. All right. So finally, that's my last slide. So possible improvements. So we would like maybe to be able to take longer step size for larger solution, perhaps using L equals the Fréchet derivative at a bar instead of the Fréchet derivative at 0, and using a Newton-like operator. So there's still a couple of things we need to handle in order to do that. But what we're working on right now is to find the wrapping effect via multi-step forward integration operator. So more like what sometimes people call domain decomposition. And that's ongoing work with Maxime Breden and Kevin Church. So we already have seen some possible improvements there, and that would probably allow us to take very long time steps and fighting the wrapping effect, which is really present in the current setup. And perhaps 2 more, 2 more generalizations. So this one is more fundamental. So let's say to try to remove that constraint involving D and N present at the beginning, and then in that case we would be able to consider more general PDEs. But that's more fundamental, and that I would be happy if someone would give me would have ideas. And finally, yeah, right now when we take very small step size, then we have kind of sensitive dependence on H on very small step size. So I think we know how to resolve that, but that's something that is kind of ongoing. All right. So, but this is exciting in the sense that I believe that there's many directions where we can improve the techniques, but it's by far not over the story. Okay, so yeah, I guess I would like to thank you all, and maybe recall that in June we'll have our first year anniversary of the seminar, and Charles Pfefferman will be our CRM Camp colloquium speaker. All right, so I would like to thank you all for your attention.
Thank you, Jean-Philippe. Let's open the floor up to people's questions.
Yeah, I can already see some questions in the chat. So Shane asked if the wrapping issue is something we already know how to handle, or we just haven't yet. Yeah, so let's say if we think we know how to handle it, because we started to work on this maybe 3 weeks ago, and we have we went back to ODEs, and then we have seen that it's probably possible for ODEs to actually handle the wrapping. So yeah, we are in good position for this one. I would say that yeah, I think we almost know how to do it. That said, Carlos asked a question, if where does the 3 in the inequality D greater than 3n come from? This well, I mean, Maxime Breden worked on on the more theoretical question of why can't we invert. Let's see where I can do that. How can't we where is that? Invert. No, I have to go to PDEs. Right. Yeah, this. Why isn't it possible to kind of invert this whole thing on the space of Fourier-Chebyshev? But that's a question which is much more fundamental than Fourier-Chebyshev. It seems to be, even if you go to Sobolev norms, or if you go to if you stay in the function space, then to be able to kind of bound. I mean, if you divide, or if you invert that operator and you put it on the left, and then you regroup all of the differential operator, then somehow it looks like there is a theoretical obstruction to be able to do that. Yeah, so okay, but we are exploring that, right? This is, I mean, this paper we submitted 1 month or something ago, so yeah, I really like this approach, but I believe that, you know, if people start chipping in, then it could be made, because numerically it's fantastic. It really works well. And the implementation is also super simple. So Javier said it feels like the natural exponent should be n without the 3. Yeah, so numerically, this constraint here is very tight, at least with Chebyshev Fourier, with the actual norm we choose. So this constraint seems to be sharp, at least numerically. So if you guys have more like a theoretical understanding of what could happen here, if we relax this, if we can find examples where if this is violated, then we cannot make it work. Yeah. It could be the matter of the basis, right? Could be. All right, there's a parallel discussion in the chat. Yeah, all right.
May I ask a question?
Yes, Michael.
Oh, you said that you use the spectral method, so the Fourier series decomposition in spatial direction. And of course, it's clear that that's your natural way to do that. But my question is, how far is this coupled to the Chebyshev decomposition, which you do in time direction? Is this using the Fourier series expansion in space direction? Is this just for convenience, or is that directly involved in the with a Chebyshev expansion in time direction?
Yeah. Well, if you look at this, so I mean, I guess there's a couple of ways to answer your question. So so for a long time, I mean, I think I started to work on that 8 years ago, and you know, for me it was just natural to do because I worked on Chebyshev for ODEs and it worked super well, and then I was okay, so let's do that for PDEs, and I was facing this problem of computing of handling the inverse of that of this type of operators. So that became, in of itself, it became a theoretical problem, right? So I was interested in trying to solve that, and I met Jacek, who worked on this. So this specific operator really comes from Chebyshev Fourier. Now, if you want to consider a PDE which has, say, a spatial domain which is not naturally leading to the use of spectral methods, you could use Chebyshev, but then you would not have this operator. It would be a combination of finite elements together with Chebyshev, and it would work. I mean, I think that the use of Chebyshev in time is definitely very strong, very strong. But let's say that operator will not be present if you do not have Fourier in space.
So, but anyway, but your strong, as you said, the strong property of Chebyshev expansion in time direction could be combined with any other spatial decomposition.
Absolutely, yeah.
So that makes the method. So you're concentrating in a sense on the time direction, and the space direction you just use Fourier for convenience. Maybe of your own experience.
Yeah. I mean, as I said, I worked on that 8 years ago, and I just couldn't do it, and now I'm just happy I can. But of course, Michael. Yes. I prepared myself for your question.
Yes.
Możemy wyjechać.
And even another way, haven't some people also looked at spectral in space and then more like a Chebyshev interpolation based methods in time? Was JB and Maxim, is this more like?
Yeah, absolutely. Yeah, more like not spectral in time, but like more like the Chebyshev interpolation. Yeah, exactly. Yeah, they've done that. Yes. Yeah, that's an ongoing project. Yes.
Another question concerning your PDE. I'm a bit surprised that we don't see any sign restriction on the highest coefficient on this alpha D.
Oh yeah, it's positive. I'm sorry. Yes, I guess it's
I'm
positive.
not sure. I think it depends on the order. So, so we should avoid something like the inverse heat equation, for example, right? Which is
absolutely.
So in the example, it's fine. So this is also fine.
Yeah. Okay, I see. But yeah, yes, I have not been very specific in the general presentation, but we do have constraints so that we have dissipativity, right? So I guess.
So I think the highest coefficient should be -1 to the power L or some L over 2, or D should be even anyway.
Right. Yeah, we have this, this constraint here that needs to be satisfied, right? And also it needs to be satisfied. I mean, there's this relationship between the alpha, so that I can use either cosines or only sines, and that has something to do with the coefficients being either, only odds or even or whatever. But yeah, I have not been I have been hand wavy here. Yes.
So essentially, this spatial part, so the minus this spatial part should be uniformly strongly elliptic. I think that's the restriction you need.
That's the restriction. Yes. Okay. Yes, I agree.
But if nobody else is asking, I have a third one. This is what you call method of steps for finding periodic solution. Isn't that equivalent to a classical shooting method? So, or multiple shooting method. So you shoot over the intervals, and then at the end you want to hit the boundary conditions. So that's what one usually calls multiple shooting. Am I wrong with that?
No, that's correct. It's like yeah, exactly. Yeah, some people call it like that. Yes. I mean, now so the only thing it's infinite dimensional, but yes, that would be a name that people use.
Yeah. Okay. So, but if you are in the ODE case, so delay, of course, then I think that's the classical shooting. Except that you now apply it to delay differential equations, which I haven't seen so far. But I think that the approach of this shooting technique is rather classical, I think. If you don't tell me.
Yeah, absolutely. I mean, I think that often I believe this is how also Piotr and Robert proved the existence of periodic orbits in Mackey-Glass. They kind of applied their techniques, and then they came back to a Poincaré map, and they closed the gap, right? So this is exactly what multiple shooting is. Yes. Yeah, the idea of this is really to move toward the idea of compact maps of discrete dynamical systems, so that we can kind of handle the infinite dimensional stable manifold using this compact map approach, and this compact map being on the level of Chebyshev series coefficient space. So that really is kind of the, in the idea of trying to prove connecting orbits between periodic orbits, then what I found in my mind, which was kind of the theoretical hurdle, was how to handle the stable manifold. And I really like this idea of using the approach of Jay and Raphael de la Llave, where they have put their hands on how to compute rigorous bounds for the stable manifold of compact maps. So that's why I kind of like this discrete dynamical system approach, because it kind of allows perhaps to enter in the world of the stable manifold, but using this discrete dynamical system approach.
Maybe just to add, so this step method or multiple shooting method, you could of course apply also to usual ODEs without delay.
Yeah,
so
sure.
To say, define your period as you like, not period, your step length as you like, and then that is also for ODEs. So this step method is just the verified formulation of a shooting method, right? Or a verified shooting method.
Yeah, absolutely. Yeah. Yeah, the only thing is that with ODEs, then you have the time step is actually a little bit more of a parameter, whereas for delay equation it is very natural. It is really just the delay, right? So it's not like a choice. It's a very it's very fundamental from the delay.
Yeah, of course, that is, except that you could take multiples of that, but it's at least a discrete choice.
Sure, yes.
Okay, any other questions this morning?
And maybe just following up of what what Michael said, did you try taking actually multiple of the delay and not the delay itself? Does this help or not with regard to the proof, let's say?
We did not, and the thing is that I mean, I guess it's probably because I didn't feel the need to it. I mean, this proof of the 12 steps, that was one of the hardest proofs I ever had to do in my life. It was it was very, I think the total size in the end was something like 10,000, or it was very tight. The fact is that, you know, when you have 12 steps, you have to fight basically the wrapping effect in the actual setup of the problem. So the norm of the inverse was 10 to the 7 or 10 to the 8. It was very large. So I did not, for this orbit, I could have explored perhaps using such an approach. I haven't done it, but I don't know. I don't know if it would dramatically help or if it would mildly help. I'm not sure.
Yeah, I mean, for me, it's not clear a priori. That's why I was asking. I mean, maybe
I didn't try it. Yeah, I didn't try it.
But my impression is that at least if the delay is very small, right, then that could be useful to take multiples of the delay as a step.
Yeah,
in this case, it's not so small, right?
Right here it is pretty small. Here it is 1/2, right? So if you look at this picture, so in the green orbit is basically, well, it's on orbit. We are in the unstable manifold here, and you know, look at the red, blue. So that's the length of the segment for the step map. So that's an example perhaps where what you're suggesting could, I mean, I don't know if it, because here it's 30 steps. I have 30 steps to reach epsilon to be 2 times 10 to the -6, which is kind of the trapping. I mean, it's kind of so yeah, with what you're suggesting, perhaps, I mean, I don't know, 10 times the delay would probably work, you know. Yeah, here the delay is 1/2 times 1, so it's 1/2. So yeah, perhaps for that it would, I mean, I don't know if it would make it work better, but it could make it just simpler, the implementation. It would just be less, you know, less coupling.
Less shooting.
Yeah, less shooting, exactly. Yeah.
All right, great. Any other questions? Well, let's thank Jean-Philippe again.
Yep. Okay, so yeah, let's see.
Yeah, go ahead.
No, I was just about to say, yeah, again, I mean, we'll have this activity, but yeah, I mean, I guess that's just me making publicity. Sorry, Jay, I should not interfere.
No. I think we're done now.
Yeah, we're done. Yes.
But maybe we should put out we have a few open spots between now and then for speakers?
Yes, we do.
So, you know, maybe if someone has something they really want to talk about, they should send us an emaal.
Yeah, or if you
or has a suggestion for a speaker rather than
exactly.
having to offer yourself.
Yeah, maybe I can very briefly quickly mention that we have open spots for April 27th and June. April 27th, May 11th, and June 8th. So for those of you who may know someone, then yeah, feel free.
If not, we'll be reaching out and twisting arms.
Almost definitely.
Okay. Thanks again, everybody. We'll see you next week.
Okay.
Jean-Philippe, very nice. Thanks a lot.
Yes. Bye-bye.